This is part 2 of mixing homogeneous mixing with two compartments. And we're in the process of deriving differential equations. We did that for tank A. So now let's work with tank B. Okay, so we're going to do something very similar. So we're going to write the rate in times the concentration in tank B. And so looking at the information we have here, as things are coming in, there's only one incoming arrow, two outgoing arrows with only one incoming arrow with information of 3 gallons per minute. So we have to scale that, and we write, okay, rate in would be given by 3, okay, and then we multiply that by the concentration. It's coming from tank A, so we have the weight in pounds x of t divided by the volume, which is 50 gallons. So the units work exactly as expected. And in other words, 3 is in gallons per minute. This ratio x over 50 is in pounds per gallon. So we can see here how gallons cancel, and this quantity has units pounds per minute. Now, concerning what leaves tank B, there are two arrows, one with information of 1 gallon per minute, another one with information of 2 gallons per minute. So let's let's write that down for the corresponding part of rate out times concentration out. So here we're going to say, look, we have information, one of the arrows is 1 times y, this is really y of t divided by 40. That's where we're expressing the concentration. And then we also have 2 times y of t divided by 40. Okay, so we could write this as simply 3 over 40 times y. And this is useful in writing the rate of change of the amount of salt in tank B as what comes in this case, this would be 3 over 50x, 3 over 50 times x, minus what goes out, which in this case would be 3 over 40 times y. So we're going to write the information we derived together, right? Each derivative, each differential equation involves both state variables x and y. So let's go to the differential equation for x, which is dx dt equals minus 3 over 50x plus 1 over 40y. And then we write the differential equation for y right below it. So this reads like this, minus 3 over 50x plus 1 over 40y. And the differential equation for y reads as, excuse me, is what we had there, 3 over 50x minus 3 over 40y. So we could rewrite the system using state variables x1 and x2, so x1 representing x and x2 representing y, and so then we could write this system of differential equations, which easily can then be rewritten in vector matrix form. So we can write the derivatives into a column vector, and here on the right hand side those expressions can be written as a matrix vector multiplication, where the state variables x1 and x2 appear multiplying the matrix here on the right hand side, and this matrix of coefficients has on the first row it has minus 3 over 50, 1 over 40, and on the second row we have 3 over 50 and negative 3 over 40. So for this matrix, we would need to compute the eigenvalues and their corresponding eigenvector. So we need eigenvalues and eigenvectors. So we can compute these eigenvalues, with a computed algebra system, and we will find that we're listing here lambda 1 v1 as lambda 1 is the eigenvalue associated with v1. And so for this 2x2 matrix, we have one eigenvalue which is negative 0.10695, and its corresponding eigenvector, it has two entries, one and the second entry minus 1.87797. And similarly, or consistently, lambda 2, the other eigenvalue, is also negative, minus 0.02805, and its corresponding eigenvector is 1 on the first entry, on the second entry with 1.27797. That means that we can write the solution, using the eigenvalue method, the solution of this system, as a linear combination that involves these eigenvalues and eigenvectors. In other words, something that looks like this: x1, x2 is summation c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2. So in other words, we could write the solution x1 of t, x2 of t as this linear combination c1 e to the negative 0.10695t times this vector plus c2 e exponential with argument negative 0.02805t multiplying this other vector. So we could use the initial conditions to solve to find the values of C1 and C2, but you could also compute the numerical solutions using differential equation solver, and this is an example of these solutions. Here you see in blue appears so both of these curves are displayed here against little t. So little t is on the horizontal axis. This is a time plot. We have initial condition x sub 2 at 0 is equal 1, and you can see how the blue curve initializes there. It kind of has a local maximum value, and then it starts decaying. And while the other solution, x1 at 0 is initialized at 5 with a value of 5, and here is displayed as a dash curve, and it starts there and starts decaying. It doesn't increases like the other curve, it simply starts decaying, and both of them are, if we were going to compute this numerical solution for longer values of time, then we would see them both approaching 0. And we know they approach 0 because if we take the limit as t goes to infinity here, right, these exponentials with an argument that has a negative value multiplying t make both of these vectors converge to, this converges to the 0, 0 vector, and this vector goes to 0, 0 as well, and added up the solutions x1 and x2 are going, x1 is going to x1 is going to 0, and x2 is also going to 0, right? So then this is what we would conclude from using the eigenvalue method in this problem, in this exercise, about mixing with two compartments.